Alright, so what I want to do for the last class of the semester is go through a way to review some material, as well as teach you a little bit more new material and see some of how things connect. So I thought I would do sequences and series. We did a lot of integration and differentiation on Wednesday. Hopefully everybody's now really comfortable with that. Let's do some sequences and series. So the first one, you might recognize 1 minus a half plus a third minus a quarter plus a fifth minus a sixth. This was what we got for the log of 2. So we looked at the log of 1 minus x, and then when we looked at the log of 1 minus x, we said, let's just plug in x equals -1. That gives us the log of 2 is this alternating series. So the question is, why does this alternating series converge? It doesn't quite satisfy any of our tests. If we try to do ratio test, root test, integral test, all of those tests fail. But there is a new test that we haven't talked about. It's the alternating series test. If you have a series of terms that alternate in sign, and they're always getting smaller, the sum has to converge. And the reason is the following. If they alternate in sign, once I add the 1/3, from this point onward, I'm going to subtract off a negative number. Because the minus 1/4 will beat the 1/5, the minus 1/6 will beat the 1/7, and so I'm going to be a little bit less than the sum from over here. Similarly, if I stop at the minus 1/4, from this point onward, everything I add on is a little bit higher. And so when you break off at the evens and the odds, you're going to be coming down towards the common value like this. This series, there's another way of looking at it, and you'll be able to see it converges. If you look at adjacent terms, 1 over 1 minus 1 over 2 becomes 2 minus 1 over 1 times 2. 1/3 minus 1/4 becomes 4 minus 3 over 3 times 4. And if you just do a little bit of the algebra, you'll actually see that if you group things together, it's equal to 1 over 2n plus 1, 2n plus 2. And so what we can do is we can see how good of a job does this series do at approximating. Oh, sorry, I'm not allowed to compile this. Sorry. Let's compile this line over here. So the value of the log of 2 is about 0.69314, and I'm having it take the first 500,000 terms in this series. So while it's computing, so we're wasting our time, do you have any rough idea of how quickly this sum is going to converge? What do you think the error is going to be? You don't have much time. It's going to finish soon. I'm looking at the first 500,000 terms. How big do you think the error is? How many terms accuracy do you think we'll get? Well, how many? 5, 10, 20, 100?
A million.
A million digits accuracy with 500,000 terms.
Yes.
Okay. Anybody else? Right now, you win the extra credit point because you're the only one guessing. Anybody have any other thoughts? 100. Okay, why only 100? That's so small. Let's think about what's going on. If you look at this, this looks roughly like 1 over 4n squared. Right? So it's roughly 1 over 4n squared. Okay. I'm about 10 to the negative 7. So you win. Alright, so I'm really not getting that many digits. I'm only getting about 7 digits accuracy. And the reason, if you try to figure out what is the sum of the remaining terms, I'm summing 1 over 4n squared from about 500,000 onward. How would you approximate the sum of 1 over n squared? What would you use to estimate the sum of 1 over n squared? What could we use? So we only had one real method to approximate sums.
Integral?
Integral test. So 1 over 4n squared should look a lot like the integral of 1 over x squared. Well, the integral of 1 over x squared is about 1 over x. Right? So I would expect to be about 1 over x. Well, actually I have a factor of 4, so I expect to be 1 over 4x. I expect to be about 1 over 2 million. Well, 2 million, that's about 6 digits. So yeah, this is actually a pretty good ballpark estimate. I expect to be about 6 digits, and 5 times 10 to the negative 7, I'm right there. So this gives you a really good idea of, does the series converge? What does it converge to? How much is your error? This is a very slowly converging formula. I've just calculated, well, not me personally, because I'm a professor, I don't have to do this anymore, I have computers. I had my computer calculate the first 500,000 terms. Okay? That's a lot of terms. You would expect you know the series really well after 500,000 terms. No, we only know it. We don't even know it to 10 decimal places. All right. The next one, I'm going to be careful not to compile the wrong line, is let's calculate pi or pi over 4. So here's the formula for pi over 4. It's 1 minus a third plus a fifth minus a seventh plus a ninth dot 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 dot. And I'm going to calculate the first 500,000 terms. Okay? How accurate do you think this will be? The clock is ticking. How many terms do you think I'll get for pi over 4? And it turns out, if you play the same game as before, this is now 2 over 4n plus 1, 4n plus 3. So you had to guess about how many digits accuracy. I'm sorry?
14.
Why 14?
There's a 2, so you just multiply by n. Yeah.
14's close, yes.
1 over a million.
Yeah, about 1 over a million, I'd say closer to about 7. If you think about it, we're going to have 1 over 16n squared rather than 1 over 4n squared. So we expect to be about 4 times as accurate as we were last time. And so when this finishes compiling, it should give us roughly 7 digits accuracy here. How many of you have seen this formula? We're going to mostly prove this formula in a few minutes. So this is called the Gregory Leibniz formula. It's going to be a nice way for us to review one of our most important series, as well as some results from calculus. So what do you think the most important series we know is? Which series do we use more than any other series? Geometric. We will use the geometric series. Okay. While it's waiting, it shouldn't take this long. So it'll be, I will just jump ahead to the next one. Now this is a strange formula for pi. I'm only going to calculate, let's see what. One term, okay, I'll bump that up a little bit. So it's the sum of 4 over 8n plus 1 minus 2 over 8n plus 4 minus 1 over 8n plus 5 minus 1 over 8n plus 6 times 16 to the n. What's the real difference between that series and the one we're looking at right above? Which series do you think is going to converge better? This one or this one? Now, this is another candidate for pi. I finally finished. So we got, again, a little bit better. Instead of 5.0, we got 2.5. Which do you think is going to do a better job, this one or that one? If I only take a small number of terms. So you want to get a sense of how quickly things are growing. So when you're looking at things, you want to get a sense of how big do you think things will be? This is looking like roughly 2 over 16n squared. These are all basically size 1 over n, but now I have a 16 to the n in the denominator as well. So which do you think is going to become small faster? The terms here, in the second one, or here in the first one? The second one. So let's see how quickly this one works. I'm going to just take 10 terms. With 10 terms, I got 16 digits accuracy. All right, let's take 20 terms. I've got 29 digits accuracy. 50 terms. I consider that pretty quickly. I've got 66 digits accuracy. Let's take 100 terms. I'll bump up the accuracy. So with 100 terms, I've got 127 digits accuracy. This is a significantly better formula. This is one of the most famous formulas to calculate pi. What's wonderful about it is it allows you to jump ahead. So in fact, I'm not going to go through the analysis. If you decide you really like computer science and you're willing to look at numbers base 16 rather than base 10, you can actually use this to calculate specific digits of pi without knowing previous digits. You can just jump and get certain digits. All right. So I can either prove the formula for pi and then do the birthday problem, or as long as I'm here, I can do the birthday problem and then do all the analysis later. First loud voice wins.
Birthday.
Birthday, there you go. Do you guys want to play the birthday problem?
Yeah.
All right. Borderline. So everybody, either right now think of your birthday, or think of a random date. Right? hopefully people don't mind just saying their birthday out loud. The question is whether or not there's enough people in the room so that we will have 2 people sharing a birthday. Okay? I have never failed when I have done this in public. Okay? And if somebody in the back row sees that we're about to fail and your birthday somehow changes a few days, just email me later. I just want to make sure before we start, is there anybody here who was born on February 29th? Okay, I have a deal with admissions not to let anybody who has been born on February 29th take any math classes with me. And they're supposed to make sure that these people sign agreements. Because why do I hate people born on February 29th?
It's more work.
It's more work, right? What do you assume about birthdays? What's a reasonable assumption? Yes?
They occur once a year.
Occur once a year. Yes? Unlike unbirthdays.
February 29th.
Yeah.
Yes, but no, okay, so, right, so okay. That's, I didn't realize you weren't being a smart ass, I'm sorry. It's been a long semester, I've gone to know you too well. Okay, so I will assume that birthdays occur once a year, and February 29th will screw things up. We don't care if you were born in the same year, so if there's somebody who, this is their 4th or 5th time taking Calc 3 with me, that's okay. You know, we don't really care how old you are, we just care what day you were born. How do you think birthdays fall during the year?
Will they fall?
I'm sorry? How do you think they're distributed among the days of the year?
Oh.
A lot in the spring.
A lot in the spring. You know, there was a biology class in here earlier. I can leave discussions like that to them. I will just say that it's mathematically simpler if we assume birthdays are uniformly distributed throughout the year. Whether or not that is true, I will not discuss. There are certain subsets of Williams College students where the birthdays are probably not uniformly distributed. Anybody know which subset?
Athletes.
Athletes. Good. Why?
Because they're, like, if they're born before like, the cutoff, they're
Right. You want to be born just after the cutoff. You want to be the oldest, biggest kid in the group that advances. Because no, what happens is you'll look good, so the coaches will think you're good, so you get more extra practice, you get more playing time, you get more attention, you then advance to the next level. There's a wonderful book called Outliers by Malcolm Gladwell, and he has this beautiful passage where he replaces the names of the hockey players in the Canadian junior championship game with their birthdays. And it's like, March 14 passes to March 7, passes to February 26, shoots, blocked by January 3, and just all days in the beginning of the year because of when the dividing line was. And one of the arguments is that this causes people to lose out on a lot of talent because certain people are shunted away. Roughly how many people do you think we need to have a 50% chance that 2 people in this class share a birthday? If you've already seen this problem before, don't answer. Any idea of roughly how many people we need?
40.
40. What about 300? You think that's too high or too low? Too high. Give me a number that's definitely too high.
365.
366.
Oh, right.
366 is definitely too high. If you're at 180, the next person has a 50-50 chance when they walk into the room of having a different birthday than everybody who's already there, or a 50% chance of walking in and having the same birthday as someone. So if you look at it around 180, each person has a 50-50 chance, if nobody shares a birthday, of causing a birthday to be shared. So I would expect it to be much less than 180. Because with 180, if I got there somehow, 1 or 2 people coming in, each one of them has a 50% chance. So just 2 of them coming in, 75% of the time, that should do it. So it should be something lower than 180. The question is how much lower? And then the question is how does it depend on the number of days in the year? I am old, so I still consider Pluto in my heart of hearts as a planet. So imagine you're on Pluto. Pluto takes a long time to go around the sun. It's got about 90,000 days in its year. How many people would you expect to be required on Pluto to have 2 people share a birthday? How does it generalize? How does 40, if it's 40, work? All right, let's go. January 21.
25. September.
May 7th.
December 1st.
August 9th.
April 12th. July 23rd.
March 24th, July 20th,
February 3rd.
January 30th.
December 19th.
January 31st.
May 7th.
October 1st. July 21st. June 17th. December 23rd.
Do we already have a match?
Yeah.
Yeah.
Okay. So we already got a match.
There you go.
Yeah, the best ever was my first year at Williams where I got a match, but it was in the last or second to last row and I was getting worried. And there was two people actually sitting next to each other. And I counted them to make sure that they really were born on the same day. And not just, using for extra credit. Not that I would mind. But they sat next to each other all year and didn't realize they shared a birthday. So here is a plot of the probability of two people sharing a birthday, at least two people sharing a birthday, if you have n people and 365 days in a year. And so this is the line 1/2. This is the probability that at least two people share a birthday as a function of the number of people in the room. And you see a little bit more than 20, around 22 is where it kicks in. Very quickly, by the time you're at 40, you're pretty safe, you're over 80%. By the time you're at 60, it's effectively 100%. So here with the size of this class, I'm pretty confident based on how many of you there are that it will work, but not absolutely confident. All right. Any thoughts as we go to Pluto? 90,000? About how many people? 1,000. About not even 100. I'm sorry, a little bit more than 100. About maybe 350 or so. And so what I'll do is I'll show you how you can figure out roughly where this should be with extremely high probability. And this will be a great way to review Taylor series and see why we care about things like Taylor series. So there's a lot of good stuff to see today, a lot of math with applications. So the first one I promised was the formula for pi. And so this is known as the Gregory Leibniz formula. And there's lots of different formulas for pi. This is a particularly good one. And then as a lot of you learned through the method of least squares, and when we did the video and streaming video, when I say particularly good, that's relative to a given metric. By good, I mean I can do the proof easily, not that it converges well. It converges horribly. But I can give the proof very simply. So consider the integral from 0 to 1 of dx over 1 plus x squared. Anybody know what the antiderivative of 1 over 1 plus x squared is? Arctangent, excellent, remember to email me. This is going to be arctangent at 1 minus arctangent of 0. And the reason is the derivative of arctangent of x equals 1 over 1 plus x squared. So we proved that earlier. This was a nice application of the chain rule. We looked at the tangent of arctangent of x equals x. And then we use that to get tangent prime at arctangent of x times arctangent prime of x equals 1. And then we solve for arctangent prime. What's the arctangent of 1? What angle has a tangent of 1?
45.
Pi over 4. Not 45 degrees because we measure things in radians, or we can't say things like derivatives of sine is cosine. So again, another nice thing to review here. We can't measure things in degrees, or we can't use differential trig without pesky factors of 2 pi over 360. What's the arctangent of 0? So what angle has a tangent of 0? 0. So this is just pi over 4. Great. So one way to calculate pi over 4 is to just evaluate this integral. Okay? Let's evaluate this integral. Does this integrand 1 over 1 plus x squared, does that look like anything you've seen? Have you seen anything that looks like this before? Geometric C is outstanding. What is R?
1 over 1 plus x. No.
So if I want this to equal 1 over 1 minus R, so what should R equal?
X.
Not x. You're close.
X squared.
You're even closer. What should it equal? Negative x squared. So if we let r equal negative x squared, 1 over 1 plus x squared is 1 over 1 minus r. Okay? So now, 1 over 1 plus x squared, well, the geometric series is 1 plus r squared plus r cubed plus r to the 4th. So this is going to be 1 plus r squared plus r cubed plus dot dot dot, which is 1. R is minus x squared plus r squared, which is going to be plus x to the 4th minus x to the 6th plus x to the 8th minus x to the 10th dot 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 dot. Okay? Now let's integrate from 0 to 1 of 1 over 1 plus x squared dx. What's the integral of an infinite sum? Who brought the engineering hat? The integral of an infinite sum is the
Some of the separate integrals.
the sum of the separate integrals. In a higher level math class, you'd worry about convergence. Let's not worry about convergence. We don't have that much time today. This is the integral of 1 dx from 0 to 1 minus the integral from 0 to 1 of x squared dx plus the integral from 0 to 1 of x to the 4th dx minus the integral from 0 to 1 x to the 6th dx plus dot 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 dot. You've got to be a little bit careful to make sure things converge. You can do this carefully. What you can do is you can truncate the geometric series at some point and estimate the error. And that will make all of this fine. The other thing, you've got to be a little bit careful about integrating all the way up to 1. Why do you have to be careful about integrating all the way up to 1? What happens when x equals 1?
It's all the same term.
I'm sorry?
It's all the same term.
Close to all the same term. Every other term is the same, and what is that value? Not 0. 1. So if I try to take x equals 1, I've got I equals negative 1. I'm now expanding basically the geometric series in a place where it doesn't converge. Technically what you should do is you should integrate up to 1 minus epsilon, get an answer, and then take the limit as epsilon goes to 0. Okay? In the interest of time, I'm not going to bother doing all this. Let's just leave it like this. What's the integral of 1 from 0 to 1? This is just 1. All right. Now I integrate x squared. That gives me x cubed over 3. I evaluated 0 and 1. What do I get? 1/3. The next one, I integrate x to the 4th. I get x to the 5th over 5, which is just 1/5. Next one.
1/7.
And there's the formula. There's the Gregory Leibniz formula. This is a formula for pi over 4. I'll leave it as an exercise as to how you figure out what pi is from here. Okay? It's very slowly converging, but it does converge. It's an alternating series, so we know there's going to be cancellations. And in fact, this is going to cancel out nicely. If you look at these, this will be 7 minus 5 is 2 over 35. And this will be 2 over 99. So you'll always get things 2 over the product of two adjacent odd numbers. And again, you can make all of this rigorous. What you do is you just truncate the geometric series at some point, you integrate up to 1 minus epsilon, and then you take the limit. Okay. Any questions on the Gregory Leibniz formula? Okay. Almost surely you will never have to calculate pi, but if somehow you are technology-less, here's at least one way you can go about doing it. Okay. Is everybody done copying this? Just the last thing I want to give you as easy of a job as possible. So what I want to do now is I want to do the birthday problem. So what class is this going to review or motivate or introduce us to?
Linear algebra.
Yeah, no, not linear algebra. Stats is a possibility.
Real analysis.
Not real analysis.
Probability.
Probability. Got to mix it up a little bit. Alright, birthday problem. We want to calculate what is the probability if we have n people in the room, at least 2 share a birthday. So P of n is the probability, actually, I'm going to write it like this. I'll do this. P sub n of n is the probability if n days a year, at least 2 in n share a birthday. I'm not going to write all the assumptions here, but we are assuming all days are equally likely, and each person is equally likely to be born on any day, and each person's birthday is independent of every other person's birthday in the room. Do you think that's a reasonable assumption? That birthdays are independent of other people. I'm married to an identical twin, if this helps.
So no.
It depends on where you are. If I'm at a gathering on my wife's side, almost surely there will be 2 people in the room who share a birthday. Doesn't really matter how many people we have, happens very often. So you've got to be careful. I'm assuming all days are equally likely, and each person's birthday is independent of every other person's birthday. You can have people's birthdays equally, you can have all days equally likely, but have some people's birthdays depend on other people. Any fans of ABBA? Anybody willing to admit it? Okay. What, can anybody tell me a little bit about ABBA? Yes.
They won the Eurovision Song Contest.
Yes, a long time ago. Who made up ABBA? What's special about the 4 people in ABBA?
They all have the same birthday?
No. There's 2 married couples that then divorced. This is one of the reasons why ABBA has not gotten together for another tour, even though they were offered, I believe, $250 million. They don't, well, be careful, this is being recorded. So you can have situations where you're choosing 2 people from ABBA, and everybody's equally likely to be chosen, but there are certain groups that would never get together. So you've got to be very careful. It's possible for each day to be equally likely, but for there to be dependencies between people. We're going to assume that that's not happening. I want to calculate the probability if in n days at least 2 people share a birthday. It turns out in probability, it's sometimes easy to calculate not what you want, but the probability that what you want doesn't happen. So if I know the probability something doesn't happen, do I know the probability it does happen? Yeah. So Qn of n is the probability don't have a shared birthday. Again, with little n people in a year with big N days. Okay? Let's calculate what this probability is. Imagine there's just 1 person in the room. What is the probability if there's 1 person in a room that they don't share a birthday with anybody? 100% or 1. There's a better way of writing 1. What's a better way of writing 1? Sorry?
1 over 1.
Not 1, okay. 1 over 1 is a good start. That's getting me there. What ratio do I want to write it as?
365.
So if we were doing the regular Earth year, 365 over 365, yes. If we're doing a year with big N days, what would it be? N over N. So just in the interest of time, I'm going to go straight to general planet and not just be anything local on Earth. All right? So that's a really good way. This is going to generalize nicely. What do you think the probability would be if we have 2 people? Well, we have n over n is the probability the first person walks in and doesn't share a birthday with anybody. Now the second person walks in. What's the probability the second person doesn't share a birthday with the first person?
And minus 1 over
N minus 1 over
n.
n. Now a third person walks in, and we want all 3 people to have different birthdays. Well, that means when the first person walks in, nobody shares her birthday. When the second person walks in, he doesn't share the birthday with her. And then when the third person walks in, she doesn't share a birthday with either one of these. So what would the final probability be? So now I need to figure out what's the probability. I've got 3 people, they don't share birthday. It's n over n times n minus 1 over n times n minus 2 over n. And so in general, if I have little n people, it's n over n minus 1 over n minus 1, dot, 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 dot. What's my final number? N minus, is it little n?
Little and minus 1.
Little n minus 1. When it was 3, I had a 2. When it was a 2, I had a 1. When it was 1, I can really write this as n minus 0 if you want. So it's actually going to be all the way down to n minus little n minus 1 over n. Yes?
Why did you write n minus 1 on the bottom?
By mistake. So all the denominators are n. The problem is this does not look very pleasant to evaluate. You've got to keep multiplying fractions like this. Okay? And so this is not going to be pleasant to plug into a calculator, but what you can do is, well, if you know what big N is, you can just keep plugging in numbers, keep multiplying, and seeing when does this hit 50%. Because when this hits 50%, then you have a 50% chance that people don't share birthday, which means you have a 50% chance people do share birthday. The problem is, if I give you 365 days in the year, you can do this. But if I give you some arbitrary number like big N, you can't just keep multiplying because you don't know what big N is. We need a way to figure out what does this product look like. Is there anything you can do to this product to make it more pleasant?
Search and replace. Can we approximate?
We're going to approximate. We're going to do something first before we approximate. What can we do to this product?
Convert it to a sum?
Good. How do we convert it to a sum?
Logs.
Logs. So again, Pavlovian response. Avoid this when you're with elementary school, junior high school kids. Otherwise, when you see a product, it should be instinctive. Take logarithms. Are we still in range over here? Okay. So the log of Qn of n is now going to be the log of n over n plus the log of n minus 1 over n plus dot 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 plus the log of n minus little n minus 1 over n. I can write this as a sum. This is the sum. K goes from 0 to n minus 1. The log of n minus k over n. Or, there's a better way of writing this. It's the sum. K goes from 0 to n minus 1. The log. How might you write this number n minus k over n? What might be a good way to write that number?
1 minus k over n.
Excellent. 1 minus k over n. Does this look like anything we've seen recently?
If we just replace k over n with a variable,
Yes, with what variable?
then that would look like one of our problems.
Yeah, it would look like Taylor series. Something we've just recently done, which will get to be on the exams, which we haven't had a chance to review because we just did so recently. Here is a way to find the answer to the problem using Taylor series. We're going to approximate this sum by using Taylor series. So recall the log of 1 minus x is equal to negative x minus x squared over 2 minus x cubed over 3. So if x is small, the log of 1 minus x is approximately minus x. Small x implies the log of 1 minus x is about negative x. Is that a perfect approximation? No. Is it a pretty good approximation? Yes. If x is small, x squared is much smaller. And x cubed is even smaller. So the real thing is, as long as k is small relative to n, as long as we don't need too many days, we should be okay. And so now we get the log of Qn of n is approximately the sum, k goes from 0 to n, well, the log of 1, so x is just k over n, so I get negative k over n. No, I'm sorry, I'm summing up to little n minus 1. I can pull out a negative 1 over n, and I have the sum, k goes from 0 to n minus 1 of k. Where have we seen this sum before? We saw it once. So we saw this when we did the fundamental theorem of calculus, when we were trying to find the area. So we had our Riemann sums, we had the upper sums and the lower sums. And after we proved the fundamental theorem of calculus, I tried to test it. And the first thing is I tested it with a rectangle. And I showed you the fundamental theorem of calculus correctly gives you the area of a rectangle, and you weren't impressed. What shape did I do after a rectangle? What was the next shape after a rectangle? So rectangle, looked like this. What shape did we do after the rectangle? I'm sorry?
Box?
I'm sorry, box? Not a box.
Circle.
Not a circle. Circle's hard.
Trapezoid.
Not a trapezoid.
Triangle.
Triangle. Triangle was the next shape we did. And we were able to get the correct answer, and we used a formula for what the sum was. But again, were you impressed that the fundamental theorem of calculus gives us the area of a triangle? No. You knew how to calculate the areas of triangles. What shape did we do after the triangle? So you can look at this as this is the equation y equals 1, y equals x. What was next? Y equals x squared. And hopefully at this point you were then somewhat impressed by the fundamental theorem of calculus. Because now it's giving us the area under a parabola. Okay? And area under a parabola, that's not something you could have done before calculus. Now, it's been a while since I've looked at the exam, but I don't really have to look at the exam to be pretty damn sure of one question on it. All right, in the definition section, what word should you be saying?
Area.
Area, right? I've been telling you, we care about integration because it gives us areas. Areas are probabilities. Here is specifically an example of the area under a curve being a probability. And if you want, you can replace this with a continuous integral, integrating the log of 1 minus x, or we can do the sum. But probability is areas. This allows you to calculate probabilities events happen. All right, so we want to figure out what is this sum equal to. And so it turns out that this sum is going to be negative 1 over n. It's n minus 1 times n over 2. And one way you can see this is you can write the numbers from 0 to n minus 1, and then write them backwards, and then add them all up. Well, I'm going to just approximate to make life a little bit easier. And I'm going to say the log of qn of n is about minus n minus a half squared over 2 times big N. Does that seem like a reasonable approximation? I've got n minus 1 times n, so rather than multiplying two different numbers, let's take the number halfway between them and square it. This just avoids having to use the quadratic formula. And if my number big N is reasonable, n is not going to be so small, this is going to be a pretty good approximation. So now I can solve. I get, this implies, I multiply by negative 2n, the log of qn of n, take the square root of this, and add a half. And that's going to be approximately n. Why am I doing this? Well, if I take the very special value of n such that this equals 1/2, that's going to tell me, what n I should take. So let n 1/2 be such that qn of n 1/2 is 1/2. That's the value of n I'm searching for. I'm searching for what's the value of little n such that I have a 50-50 chance. Well, if I have a 50-50 chance, this probability is supposed to be 1/2. So that tells me my special value of n is approximately 1/2 plus the square root of minus 2n log of 1/2. What's the log of 1/2? How could you rewrite that? The log of 1 minus the log of 2. The log of 1 is 0. So this is the same as negative log 2. Oh good, the negative sign cancels. You should have been maybe a little worried. I've got a negative sign here. I shouldn't be taking the square root of a negative number. Turns out we're not taking the square root of a negative number. Why? This is a probability. Probabilities are between 0 and 1. So this is going to be the log of a number less than 1. It's going to be a negative number. So since it's a negative number, negative times negative is positive. So it tells you that the answer is going to be roughly 1/2 plus the square root of 2n log 2. Okay? So what I will do is, what value do you think we should take for big N? Any thoughts as to what value we should take for big N? How many days should you take in the year? 365, right? So take 2 times 365 times the natural log of 2, and this gets, it's about 22.9. And so if I go back to my original function, 365, 22, 365, 23. So if you have 22 people, the probability of a tie is 47%. With 23 people, it's 50.7%. So 22 people, 47% chance. 23, it's 50.7%. Good approximation or bad approximation? We took this massive product and we were able to evaluate this product really well. We got 22.9. I could have done a little bit better if I wanted to use the quadratic formula. Is it hard to use the quadratic formula? That would improve it a little bit. As a nice exercise, go through and see what you would get by using the quadratic formula. You know, do I need to do that approximation? No. But I want to try to keep the camera crew happy and not have to go to too many boards and go all the way down there. Also, there's a limit to how much algebra you want to see. You want to do better? By all means, do a little bit better. Could we do even better? Sure. We could actually take the next term and see what kind of correction it would give us. We'd have to then figure out what's the sum of k squared. We can do that. We saw that for the parabola. We could actually get the next term as well. So this is another one of my favorite problems. I have a couple of problems I collect over the years. I really like the problem we did on Wednesday. That one problem reviewed so many different concepts. Gave us Lagrange multipliers, gave us maximization, gave us the first and second derivative test, gave us plotting functions. Lots of great stuff in that problem. The birthday problem has a lot of great stuff as well. It gives you applications of calculus. Why do you care about these things? It gives you how do you calculate simple probabilities. It also gives you how do you formulate a good problem. A well-posed problem. There is the danger of people born on February 29th. There is the danger of identical twins. There are some identical twins on campus if they happen to take a calculus class. Well, okay, for me, I'd actually be happy if they're taking a calculus class with me. Right? That makes my life much easier, and I'm far more willing to bet. Right? And then it gives you an idea of why do we care about Taylor series. And so this is probably the best way I can justify why we care so much about Taylor series. If I give you specific numbers, you can grind away. How many of you are taking economics or considering being an econ major? Good luck in your upper level classes. You are going to have extremely complex models with questionable assumptions at best. And the models are going to be too hard to solve. There's just too many things going on. So what you have to do is you have to resort to numerical simulation. So you maybe choose what the federal tax rate should be. You can choose what various interest rates are, and then you see what happens. And then you want to know, well, what would happen if we did a tax cut? What would happen if we did a tax hike? What would the effect of this be? What if we changed the margin requirements? And unfortunately, these problems are so involved that the only way you can really get answers is to run numerical simulations. And it's very expensive, it's very painful, it's very time consuming. If at the end of the day you can get a formula that depends in a very nice way on the parameters of the problem, you can say, oh, well, if I increase the Federal Reserve rate by this, oh, here's how it changes. This is very similar to the lecture I gave you on sabermetrics, the Pythagorean one-loss formula. which predicted a team's winning percentage just from the runs scored and runs allowed. If you now hire, a really productive ball player, we have ways to estimate what their run production would be and how much would they contribute. Or if you hire, if you sign a really good pitcher, like the Yankees have done with Tanaka, you can estimate how many runs he will be saving your team. And you can get a sense of how valuable is this person. And you don't have to resort to simulations. You have this beautiful formula. You can adjust the parameter of it. I now allow 23 fewer runs in a year. How many wins will that transfer to? How much is that worth to me? And there are ways to assign values to different wins. If you're like the Houston Astros from last year, does it matter if you win 5 or 10 more games?
No.
No, people won't even notice. Your record is so abysmal. The Astros lost more than one fewer than 1 out of every 3 games last year. What if you're a team that just misses the playoffs? If you win 5 more games, is that worth something to you? Yes, now you're in the playoffs, now you have a chance at the World Series. Even if you don't do that, you have playoff revenue. So wins are worth different amounts of amount in different places in the season, depending on how your record is. And so if you have a good way of assigning the value of somebody when you're signing them, you know how much money you're willing to pay. So the value of a ball player is not independent of the team that is bidding for them. Different players are worth more to different teams. Here, what I love about this answer is we now have a beautiful formula. The number of people we need as a function of number of days of year is approximately 1/2 plus the square root of 2n log 2. Or if you want to, you can migrate the 2 inside and just call it, n times the natural log of 4. It says the number of people is growing like the square root of n. There are enormous applications to this. This is not just a cookbook problem as to who cares about people who share birthdays. This actually has applications in cryptography, in trying to crack codes that the other side has used. Can anybody think of other good questions we could ask related to the birthday problem? So the question I asked is, how long do you have to wait for there to be a 50% chance that 2 people share a birthday? What other questions could you ask?
How long till it's 100%?
How long till it's what?
100%?
Well, so that's going to be 366. So you want to quantify it. How long until it's a given tolerance? Maybe 99%. Something like that. What's another question we could ask? I don't want to gamble. I only want to take certainty. So 99%, yes.
Home states.
I'm sorry?
Home states.
Home states. So we could change from people birthdays to states.
Because it's 3 people have the same birthday.
Well, how many do I need to have 3 people share a birthday? Right? I think once I actually had a class with 3 people sharing a birthday. What else could we have? Instead of having 3 people, we could have
N people.
We could have n people. We could have 2 pairs of 2. Another more interesting one is which person, as they enter, let's imagine people enter the room one at a time. Which is the person who's most likely to cause a shared birthday? So here we got it, I think, somewhere in the 3rd row. Where do we expect that to happen? Who do you expect not to cause the shared birthday?
The first one.
The first one. First one is right out, it's like the 5 from Monty Python, not going to happen with the first person walking in. By the time we get to the 22nd, 23rd person, do you think the 23rd person is the most likely person to cause a sharing? Probably not, because we've got basically about a 50% chance. We even have a 47% chance before them. It's quite likely a couple of times we're going to have people before them causing the birthday. So it's an interesting question as to where do we think the most likely thing would be. All right, this is a good place to stop. I will deal with the administrative stuff after.